Hello, in this quick video here, we're just going to have a look at a different kind of linear equation. So far, we looked at ones which have only one variable, whether it be x or t or whatever else, but you can also have linear equations with two variables, and they often make up what are called linear functions. So as I said here, more than one variable, and when they do, the variables have constant proportionality. And what that means is that as one variable changes, the other one changes at the same rate. And I've got some examples here to try and show you what I mean. This is a classic linear function, y equals 2x plus 1. And if I did a little table of values of x and y, when I substitute the values 0, 1, and 2 in, I get values for y of 1, 3, and 5. And can you see that as x increases by 1, y is increasing by 2 constantly. It's constantly changing with a value of 2. So that's what tells us that it's a linear equation, that constant proportionality to each other. Let's go down to the bottom here where I've got y equals 3x squared. Again, we can see that it's not a linear function because we've got a square in there. But also have a look at the relationship between x and y. As x goes up by 1, have a look at what's happening to y. Between here and here, it's gone up by 3 units. But between here and here, it's gone up by 9 units. And so the increase is not constant, and therefore they are not linear equations. These ones here are all linear equations. These three here are all linear equations, and in fact they are the same equation. They've just been written in different ways, but they are all the same. Okay, whereas this one is not linear. Okay, so here's an example from the textbook. You'll be doing some work from exercise 16b, so at the other side of the textbook. And in this, we're just looking at modeling this relationship, this linear relationship between two variables, and maybe doing a little bit of solve work as well. So here we have our example here. I'll just highlight the critical parts like I've been doing. So a car travels from Copenhagen to Charlegem, which is a distance of 150 kilometers in 2 hours. Assuming that the car travels at a constant speed, draw a distance time graph and calculate the speed. Okay, so we need the graph and we need the speed. Now that word constant speed is really important because when you see the word constant, you can think of that constant proportionality. Now looking over at slide 10 there, you can see that I've got a bit of a graph starting up here. So I'll just put arrows on it like all good graphs should have. And I can't have negative distance or negative time, or not in this particular context anyway. So I haven't bothered with doing tails on my axes. We'll make this corner here O for the origin, the place we're starting. And we will make the vertical axis the y-axis, which is pretty typical, and the horizontal axis the x-axis, remembering that the horizontal axis is always the independent variable and the vertical axis is always the dependent variable. I could just as easily have used t instead of x for time and d instead of y for distance. That would have been quite appropriate as well. If you have a look at the textbook, they have made t in minutes and d in kilometers. I'm not too sure why they use t in minutes. I'm not going to. I'm just going to use it in hours. It makes more sense to me because speed for us is almost always kilometers per second or kilometers per hour or meters per second. So I'm just going to sort of say, well, I know what I've got. I've got 2 hours. That's my fact from my question. And I know that in 2 hours that they've traveled 150. So I'm just going to go up and then across, nice and straight, isn't it? That's perfect. And there's 150 labeled out there. And so my graph would be, now this is a bit, let's see how this tool goes. It would be a straight line going from 0 to 2 on the x-axis and 0 to 150 on the y-axis. That's our distance time, and it's a relationship. And what we can do is we've got because it's a constant speed, the rate is the same across that whole distance. It's proportional to each other. And so I can read values off it. So I'll do it in a different color. So for example, if I halve the distance here, sorry, I'd halve the time here, I've got 1 hour. And if I go up to the graph and across here, if I was using actual graph paper, I could see it for real, but I can also use my common sense and say, well, it's a constant proportionality. So if I've halved the time here, then I've halved the distance here, which is where I get 75 from. So that's what a graph is good for, I suppose. A straight line graph, linear graph, constant proportionality. Now we should answer the question. Have we drawn a distance time graph? Yeah, that does it. Have we calculated the speed? No, but we can do that pretty handily, can't we? So I'll just put in slide 12 here. I'll leave it in blue. Therefore, the speed is equal to, well, speed is kilometers per hour, and quite handily, I've already marked off 1 hour and 75. So if we want to, though, just to be a bit complete, I can say is 150 kilometers per 2 hours, which is equal to 75 kilometers, 150 divided by 2 per hour, or if you like, 75 kilometers per, hour to the -1. Either way, you have worked out the speed. Okay, I'll leave it there. Have a go at doing some problems yourself, and we'll take it from there.